Alrighty, well, we're at our appointed time, so we'll go ahead and get started. Welcome to the session on TCP Selective Acknowledgement. I'm John Pittle, Services CTO at Riverbed. And what I hope to cover in this session is I'm going to call out some specific RFCs. We're going to review some TCP basics that we need to kind of set the stage. Then we're going to jump into an introduction of selective acknowledgement. We'll look at some decode details. We'll look at some examples. We're going to particularly look at some nice Wireshark features around adding columns to views, filters, and colorization of the view. And then I have a real-life capture of some very significant SACK activity, what I call adventures from the field, and we're going to step through that. That should take about 10-15 minutes, and then we're going to wrap up. I've asked the moderators to give me a heads up at about 5 minutes before we're ending, so I can kind of make sure we're wrapping up and then leave time for Q&A. So a little bit about me. I've been practicing performance engineering since the early 80s and working with different protocol analysis tools since the early 90s. I've been with OpNet/Riverbed since 2005, and something that I truly enjoy is a mystery, particularly complicated performance issues. So using Wireshark, being involved in performance engineering, it's a perfect fit. And I no longer have the beard, as you can tell. It's changed colors. I've trimmed it back. So that was shaved off in 2003. So that's a little bit about me. Let's go ahead and get started. So I'm not sure how many folks in the audience would spend a lot of time reading RFCs. They can be intriguing. They can be filled with drama and intrigue. But I do want to just point out RFC 793 is a great place to start. It's the foundation of everything to do with TCP. Many things have changed, of course. But that particular RFC kind of gives you a flavor for what the intent was, how it was intended to work, why it was intended to work that way. There's some good background. And then in roughly 1996, a new RFC came out, RFC 2018, and then there was an extension to that 4 years later, RFC 2883. And to be honest with you, I haven't checked to see if there's been even more updates. It's quite possible. But these are the three key ones that I would encourage you to take a look at. Just if nothing else, review the table of contents, see what's there. And then of course, do a Google search to see if there's any extensions past RFC 2883. So for us to get started to learn about selective acknowledgement, we need to take just a couple of minutes in baseline understanding around general TCP ACK behavior. So hopefully everyone in the session is aware of some of these details. As long as packets arrive in the expected order, the receiver will ACK every other packet. That's a default behavior. It can be changed, but the default is to ACK every other packet. However, if a packet arrives out of order at the receiver will detect that and then immediately issue an ACK with the value equal to the sequence number that was expected, not the sequence number that was received, but the sequence number that was expected. And herein lies some of the problem. The host that sent the data doesn't know what was received. All it knows is, hey, the receiver's telling me he didn't get what he expected. So that behavior is going to continue. The receiver is going to continue to ACK every packet until the expected packet is received, and then the receiver will go back into the normal every other packet behavior. If the sender of the data receives 4 ACKs in a row from the receiver, we call this a triple duplicate ACK, and at that point the sender will retransmit the missing segment if fast retransmit and recovery is available and enabled on the sender. So these are just some very basic baseline behaviors. And we'll take a quick look at some of the Wireshark decodes for that basic behavior, because I want to introduce some terminology and make sure everybody has that terminology solid. So the terminology I want to make sure is clear for everybody, and would even ask everyone to start using this terminology, is the term cumulative ACK, and that's the original definition for ACK, cumulative ACK. And the reason it's called cumulative is because it reflects a value that represents all stream bytes received in order, and in order is underlined for a reason, in order up to the point when the ACK was transmitted. So the receiver is basically saying, I have, when the receiver sends an ACK, he's basically declaring, hey, I've received everything in the TCP stream up to ACK -1, and I'm now ready for the next segment of the TCP stream, starting with a sequence number equal to this ACK. So on the screen, we've got ACK equals 40. Relative, this is with Wireshark relative numbers. So I've received up to 39 relative, and I'm ready for sequence starting at 40 in the TCP stream. So that's cumulative ACK. It's important to use that term because as we introduce selective ACK, we want to be able to compare and contrast the two. So now that we have that baseline, let's cover some new information about selective acknowledgement. So there was a new RFC. It's a proposed enhancement to TCP. And the idea is that we want to be able to selectively acknowledge segments that have been received out of order. So this is a new concept. Previously, we were only allowed to say what's been received in order, and now we have an opportunity to signal back to the sender that we've received something, it was not what was expected, and here's the details about what we've received. So we can't do that with the cumulative ACK. And so a new field is needed in order to handle this. So the protocol enhancement was to take advantage of using some space in the TCP options field of the TCP header. And we can actually track and report the receiver of data can report and signal back to the sender that we've received up to 4 out of order segment or segment ranges using SACK. Now that number 4 is reduced to 3 segment ranges if the TCP timestamp option is also being used. And that's because there's only so much space in the TCP options field. There's, if you're not using timestamps, we can squeeze in 4 SACK ranges. If we are using timestamps, it's just 3. So how do we turn on selective acknowledgement? Well, it's typically on by default these days. It certainly wasn't in the early days, but it's on by default in modern stacks. It's negotiated at connection startup. So if you look at the SYN and the SYN-ACK, you'll see SACK permitted, which means, hey, I will process the SACK field if you send it to me. And it's interesting that each side could independently choose whether or not they will support SACK. But you'll see it in the SYN and the SYN-ACK packets. And of course, just kind of recapping, The intended benefits is to give the sender better intelligence about the success of packet delivery based on what we're hearing back from the receiver via the ACK mechanism and the selective ACK mechanism. And what we're hoping to do is minimize the amount of unnecessary retransmissions. If we can know that, hey, there's a segment missing, but there's 4 segments after that that were received, we don't have to retransmit those other segments. We just need to retransmit the missing segment. But the little key here, I'm going to try my magnifying glass. All right, there's my magnifying glass. The key is this third bullet here, which indicates that with SACK enabled, it does not mean that the sender is going to change any of the congestion control algorithms that are present in that stack. So even though we're retransmitting less packets, hopefully, any retransmission could still have a negative effect on the congestion window and all of the related timers. So we're going to learn how to interrogate the SACK fields. It's going to help you quantify the extent of out-of-sequence packets, and depending on the nature and the timing of those out-of-sequence packets, there very well could be retransmissions. We're going to see a lot of that in our adventures from the field. But during our Wireshark sessions, there's some great features for interrogating the SACK fields. We're also going to use bytes in flight is another guiding metric for determining how bad is bad in terms of the nature of the out-of-sequence packets and whether or not it's impacting the congestion window. And in quick summary, if the in-flight data, if bytes in flight stays high, then we really don't have too much of a performance issue being caused by out-of-sequence packets. However, if bytes in flight data consistently dips or hits 0, chances are you're going to frequently see TCP slow start, which is a standard congestion control mechanism. And with the SACK field and in bytes and being able to detect slow start, you'll be able to see how much of the issue is caused by out-of-sequence packets, which is fixing that in a network is different than fixing packet loss due to a bad transceiver or class of service queues that are being overwhelmed, etc. And I think I'm almost ready for a question. Let me see what the next slide is. Yeah, so I'm going to stop here on this heads up, new terms coming. And do we have a question in the chat window?
Yes. In the Q&A window, we have one question.
Q&A, yeah.
Yep, from Jeff Arono. How does window size and window scale impact the 4 duplicate ACKs resulting in retransmit?
Hey, Jeff. Hi, good evening. Thanks for that question. I don't really think that the window size and scaling impacts the duplicate ACK mechanism. They're really two different items. So receive window size and window scaling is more about how much buffer space do I have available and how much can the sender send without overwhelming the receiver. I think to some extent, if the window size was super tiny and there was no window scaling, then probably just the receive window mechanism itself might prevent too many segments on the network at one time anyway. So in general, it wouldn't impact it unless it was unusually super low, in which case you would never get enough segments on the network without an ACK. Hope that helps. Next question.
Yeah, from Maz. He is asking, or she, should we look at bytes in flight from sender or receiver side?
Great question because they look very different whether you're on the sender or the receiver. So you're going to want to look at it from the sender side, not the receiver side. And is there another question there?
Yep. Ramon is asking, I was not clear on if retransmission for SACK will affect the congestion window or not. Could you expand a bit more on that, please?
Sure, sure. So the retransmission, separate retransmissions from this selective acknowledgement signaling mechanism. So SACK is a signaling mechanism to let where the receiver is informing the sender, hey, I'm receiving things out of order, just wanted you to know. And oh, by the way, I'm still waiting for the segment at the cumulative ACK. So the sender is going to retransmit hopefully as few segments as possible. And depending on, I'm going to say, the state of the congestion window at the time, if we've seen no packet loss and no reason to retransmit up to a given point in time, then the congestion window would hopefully just, reduce by half and then merely go on its way until it finds another retransmission, in which case it may reduce in half again and eventually get to slow start. So the fact that SACK is there doesn't really change the behavior of the congestion window mechanism. SACK is there to hopefully reduce the amount of retransmissions necessary. But as I pointed out in that one slide, it will not change the congestion and packet recovery behavior of the particular TCP stack that's on the sending machine. So I hope that helps. Usually I like to see people's faces when I'm answering questions, because then I can tell if it's like, did that make any sense or was that just totally confusing? So I just have to hope that that was helpful. And then I think we'll just take one more and then we'll have to continue on and we'll pick up at the next Q&A checkpoint.
Great. So this one is, you mentioned CWND. Is it the amount of TCP segments that sender will send without waiting for ACK from receiver?
I don't think I mentioned that specifically. The answer to that is a little more tricky, and I'm not quite sure how I'm going to relate it to what we've just been talking about. So the congestion window is the potential amount of segments that I could put on the network as long as the receiver has plenty of space. The congestion window we can't really see. It's not, we can see the receive window, we can infer the congestion window. So the question is it the amount of TCP segments that sender will send without waiting for an ACK from the receiver. So that's a good question. Now I understand it, and the answer is yes. If the congestion window is, let's say, 10 segments big, the sender would be very happily sending 10 segments. And if those are successful and there's enough receive buffer, we might even bump that up higher. As long as we have enough send buffers, enough receive buffers, and the network is stable, then yes, we would do a burst, what I would call a burst of packets, congestion window size. So that's actually a great question and pertinent too, because when do we get in trouble with out of order packets? Oftentimes it's when there's a pretty significant burst firing out all at once. Okay, so let's continue on. I'm going to save, I know there's one question outstanding. I'm going to save that for our next checkpoint. So we've got, I'll just kind of want to make sure everyone's clear. We're about to introduce 3 new terms on the next slide. So buckle up, here they come. So Wireshark can decode the SACK fields. I mean, it decodes just about everything. And of course the SACK fields are no exception. And what we're going to see is we're going to see a SACK count, which I really should have put in brackets because it's a Wireshark value add field. It's not actually, I don't believe it's actually in the options field. Left edge and right edge are in the SACK block of the options field. So we're going to be seeing left edge, right edge. We're going to see a lot of this left edge, right edge SACK count as we continue on. And we're going to start with an illustration to really lay a foundation for those terms, left edge, right edge. So in our first illustration, we've got a burst of 5 packets. So to our person with the congestion window question a few minutes ago, let's assume congestion window is at 5 and we're putting 5 segments out on the network. And they left the sender in order. So we had sequence starting at sequence 11 for a length of 10, 21, 31, as you can see there. So they all left in order, which is pretty much what we expect to see. However, due to a network issue, the packets are received in the following order: packet 1, 2, and then 4, 5, and 3 comes in last. So let's kind of look at how would we visualize that from a tracking TCP segments and the stream byte pointer. So the first 2 packets arrive. We're at the very, very beginning. We're at byte 11 of the stream all the way up to byte 30. And all of a sudden, packet 4 shows up. Now we're expecting a segment that starts with 31, but what we've received is 41. So we flag the left edge of that new segment in packet 4 as left edge 41, and right edge, kind of following the same behavior as the cumulative ACK, we're going to be +1 of what we were what we've received. So it's really what we would expect next to that right edge. So packet 4 arrives, packet 5 arrives. Notice that the left edge does not change because all we've done is we've added a segment to, we've incremented 1 segment to the stream, and now the right edge has been changed from 51 to 61. And then here comes packet 3. All data's been received up through and including byte 60, and now the receiver is ready for TCP stream byte 61. So this is our first illustration, kind of a visual, very simple, very basic. We want to really drive home these concept of left edge, right edge. So I think we have another example, but first we're going to look at some decodes. So we're going to start with some decodes. So I've highlighted, I'm going to use my magnifier again, unless we hear back from the audience that it's distracting. So I've highlighted packet 38 on the screen for no specific reason other than it does have a SACK field in it. And notice that the cumulative ACK is at 14771, which means I've received all the bytes up through 14770 in relative terms. And I'm ready for 771. But there's some additional data here. The additional data is this SACK block down here in the bottom left-hand corner. So here's a SACK block. It has a particular TCP option kind. So it's the kind of option. It's a SACK option. It's 10 bytes. And notice that SACK count is in brackets, which again is a Wireshark, oh gosh, I just lost the word I want. Not a nomenclature, but it's a way that Wireshark uses to denote this is a value that Wireshark is calculating for you. So the additional information is, hey, I've also received 1 or more segments out of order, starting at 17619, going all the way up through 19042, and what I would expect on the right after that segment would be 19043. So here's an example in the decodes where you can see the SACK field. You can see that the cumulative ACK is there, as well as the SACK. And we're going to look at some additional examples here momentarily. So I kind of wish there was a way to do a pop quiz. I haven't quite figured out a way to make that work yet. You know, what I'd like to do is have everyone think for a minute about what's missing. Now that we know we have cumulative ACK up through 14770, and we have the selective ACK that starts at 17619, what's actually missing from the TCP stream? And we can do some simple math if we just subtract 14771, which is what we were expecting, from 17618. So that's the, or 17619. So that's the stream bytes that we're missing. I didn't do the math. It looks like it's, oh gosh, I don't know, 2,900 bytes, something like that, ballpark. But if you do the math, then you know exactly what's missing. And now if you were the sender, you'd be in a great position to figure out what you need to retransmit if you need to retransmit something. One thing's for sure, you don't need to retransmit the stream starting at 17619 because this receiver has said, I've already received that. So let's now take a look at a couple of nice features. So this, anybody who's new to Wireshark, and if you took the classes earlier in the week, you would have come across this. It's such a great feature, allowing you to customize your own views in the decode summary. So basically you right mouse click, you navigate to the option, to the field that you want, right mouse click, and then apply it as a column, and it gets added to your view, whatever field you're pointing at. So in this case, it would be the left edge. We're going to look at some more of that in just a minute, but I want to very quickly marry up what we just saw with some receiver side TCP mechanics as well. Going back to our example of the 5 packets, 1 and 2 were received, 3 did not get, 4 came in before 3, then 5, and then 3 came last. So packet 1 arrives, and part of the reason I wanted to go to this segment here is I want to make sure we think about the delayed ACK timer. So packet 1 arrives, receiver starts the delayed ACK timer, waits for a second packet. So you can see sequence number 11 came in for a length of 10. Packet 2 arrives, and immediately the receiver cancels the delayed ACK timer and sends an ACK for 31, saying, hey, I'm ready for stream byte 31. Packet 4 arrives, but it's out of order, so we have to immediately issue an ACK. And what are we gonna send? We're gonna send the cumulative ACK of 31, saying, hey, this is what I was waiting for. And oh, by the way, what I just received, since there's only one field in here, what I just received is 41 through 50. And then packet 5 arrives, it's also out of order. So the receiver has to issue another immediate ACK because it's not what we were expecting. We were expecting 31, we got something else. So now we populate the SACK field with 41 through 61. And what's kind of interesting here to think about is the receiver is holding potentially up to 2 packets in the receive buffer and cannot hand it off to the application layer. And I don't remember if I put a question in here, I didn't. And the reason that it cannot hand it off to the application layer is because we can only deliver to the app layer things that are in order. And right now packets 4 and 5 are out of order. So I can't give the stream bytes I can't give these new stream bytes to the app just yet. I have to hold on to them in the receive buffer. And that concept is important because if there's a lot of out of sequence and other factors like high latency, we could see receive buffer stress on the receiver. So packet 3 finally arrives, and now we're able to issue an ACK saying, hey, I'm ready for sequence byte 61, and the good news is order's restored to the force, everything's in order, and now we can provide that data up to the application layer. So I've got 2 questions before we get into a slightly more complicated example. Tally, can you help me with those questions, please?
Sure. Winston is asking, if the packet transfers through multiple routers or switches, can these devices affect the SACK?
Well, great question. I have a slide coming up or in the appendix about firewalls that will change that'll change sequence numbers in the TCP header. And in the early days, those firewalls would not necessarily change these, make adjustments to the SACK field as well. So I wouldn't say routers and switches would do it because those are layer 3, layer 2 and layer 3. This is a layer 4 artifact, but firewalls for sure have the potential to not adjust them accordingly, especially if they're doing sequence number randomization. Okay, is there a maximum SACK count and what affects this count? So there is a maximum SACK count. There's room in the TCP header field for up to 4. And as long as there's no TCP timestamp, we can fit 4 SACK blocks into the TCP options field. If we have timestamps, then we can only fit 3. So we're going to look at another example. I really want to draw the basics here. And this example is going to be a little bit more complicated. It'll be a little bit, I'm going to use the word uglier. And we have a sender in this case who has sent a burst of 6 packets out into the network. You can see the sequence numbers in the length fields. But due to a network problem, there's a lot wrong here. The packets are received in the following order, 1 through 4, 5, 2. So pretty messy here. We probably have a IPS or an ID, an IPS or an IDS that's potentially messing with packets, or a firewall for that matter. So they're received in the following order. We're going to put ourselves into the human canon and see if we can follow what's happening here. So we're going to climb into the canon together, see if we can sort this out, and hopefully come out on the other side. So packet 1 arrives. We start the delayed ACK timer. Don't send an ACK yet because as the receiver, we need 2 packets as long as they're in order. But packet 3 arrives and it's really not in order. It's out of order. So we're going to immediately send an ACK saying, hey, we're waiting for stream bytes starting at 21. And oh, by the way, we received 31 through 40. And then packet 6 arrives. So now we've got another block that we have received. It's not contiguous with the first block that we've received. We've kind of got 3 different contiguous blocks and we're missing a bunch. So with ACK 21 and SACK 3141, 6171, we're able to paint this picture for the sender once the sender receives this ACK. So here comes packet 4, and notice now that we're able to adjust the right edge of the first block. Notice it went from 31 to -41, and now it's 31-51, which lets the sender know that, hey, we did receive something, and oh, by the way, you can now figure out what was received with the value of the SACK field. Now here comes packet 5, and notice now we went from 2 SACK blocks down to 1 because the packet number 5 filled in the blank. I'm just going to go back one slide. Packet 5 is going to fill in this empty slot right here for us, which is going to be very nice. So now, next slide, we can see packet 5 arrived. There's still a gap, and I'm still waiting for 21, the sequence starting at 21, but I did receive 31 through 70. So that's the good news. I have received some stuff. So we can't really, usually I would do this in the classroom where I can see people and they can call out answers. How many packets are in the sender's retransmit queue at this point? How many packets? And I'm going to kind of just go with, well, this one has to be there because it hasn't been acknowledged. This one is still there. This one is still there. This one and this one. So there's actually 5 packets still in the sender's retransmit queue. And how many packets are in the receiver's queue? Well, the 4 that came out of order, I can't hand them off. I don't know for sure if we've handed off 11 through 20. If there was a push bit, we might have handed it off, so I can't say for sure. But the 4 that are out of order, I'm stuck holding on to those in the receive buffer until we get the missing piece of the puzzle. And here comes the missing piece of the puzzle. Packet 2 finally arrives. And now we don't have to use SACK anymore because everything's in order. And we're now signaling back to the sender, I'm ready for sequence starting at byte 71. So everything is back in order now. We've explored having 2 SACK blocks and what that looks like. And yay, we made it. We can now get shot out of the cannon. We came through the other side. So let's look at codes dealing with multiple blocks. So notice that in our summary view, we have this kind of funny condition up here. We have TCP SACK left edge with 2 numbers and TCP SACK right edge with 2 numbers. We are getting the information, but it is a little bit confusing to look at. And we're gonna, in a second, explore how to fix that. In the SACK section, the TCP options, we can see now there are 2 blocks. So I've highlighted row 42. We're looking at row 42. There's 2 blocks that are being represented, and you can see the left edge, the right edge for block 1, and or instance 1, and the left edge, right edge for instance 2. And you could literally do the math and figure out what's missing, how many bytes are missing, etc. So here's a zoomed in view of that. Nothing really different other than you're now seeing 2 blocks being defined. And in this view, I've applied a different Wireshark profile, and notice now that we've separated out left edge and right edge into left edge 1, right edge 1, left edge 2, right edge 2. And it's a really great feature of Wireshark, and I'm grateful to Saki for showing me this a few years ago when I posed the question of how do I get rid of these stupid commas. And it's been very eye-opening, and here comes the cool feature that allows us to do that. So when you edit a column with Wireshark, you're going to see an occurrence field here. The default there is 0, which I'm guessing really means all instances of whatever that field represents. In many cases, most fields, there's only one instance of a value. But if you think about a tunneling protocol, let's say like GRE tunneling or CapWAP tunneling, or those are the 2 that come to mind. There's and if you think about IP ID numbers, you've really got an IP packet inside of another IP packet. So there's an inner and an outer IP ID number. I'm using that as an example. And that's another case where occurrence number is really handy. So there's a bunch of places where occurrence is super handy. So we've looked at some illustrations. We've looked at creating columns. We've looked at segregating out the different occurrences. And I think, oh, one more thing before I go to Q&A. So something else that's just, I have to tell you, I've worked with Wireshark for a lot of years. Probably in the last 4 years, I've just dug deeper. I mean, you can get a lot out of Wireshark just kind of at the surface level, but what's really exciting, and I would encourage everyone, is to dig deeper, dig around, play with profiles, play with views, play with colorization. So here's an example of filtering and coloring, and you know, it's pretty straightforward once you get used to it. You know, I've created a coloring rule called SACK1, and if a packet meets this criteria, we're going to color the row yellow. Clearly SACK2 is going to, whoops, I can see I forgot to rename that. That should say SACK3. You can see orange is if there's 2 SACK fields, and red is if there's 3 SACK fields present. And here's an example of what that looks like. Now, in this case, it's like, all right, there's a lot of noise in this particular capture, but in terms of out of sequence. But it's really nice if these were spread out, you know, if there was a really random pattern of out of sequence packets, using colorization really draws your attention to the areas where there's burst. You know, if the out of sequence, if the pattern of out of sequence packets, if there is a pattern, using colors will help you to quickly identify that pattern. So we're ready for adventures from the field. Do we have a question before we go on?
Yes. Jeff is asking, with SACK, what triggers a retransmit? Does it have to be 4 identical SACKs?
So, so I think I've covered this, but perhaps I didn't cover it well enough. So SACK is just informing the sender what's been received by the receiver. What causes the retransmit is it's the duplicate ACK mechanism. Actually, as long as fast retransmit is enabled on the sender, then we'll be able to do fast retransmits based on 4. So it's not 4 identical SACKs, it's 4 duplicate ACKs with the cumulative ACK field being duplicate. So typically when you see, and we'll see examples of this coming up, when you see the SACK field, you see the cumulative ACK not changing, but ACKs keep coming out, I can pretty much promise you that the SACK field is going to be changing inside of the TCP header. But it's the 4 duplicate ACKs in the cumulative ACK field that causes a retransmission if fast retransmission is enabled on the sender. If fast retransmission is not enabled, then you want to make a note to yourself, let's get it enabled. But then it would be a retransmit timer that causes the retransmit. So not really having to do anything to do with SACK per se, but it's duplicate ACK of the cumulative ACK. Right, I hope that helps. So we're going to dive now into what I think is an interesting example. It's pretty hardcore, lots of out of sequence packets. There's a little bit of setup to help explain what it is we're going to look at. And I'm going to try to go through this quickly because we've only got about 15 minutes left. So the setup, I'm going to move through pretty quickly, and then we're going to get into the actual content. So we're going to look at an actual troubleshooting engagement I did a few years ago. And here's the scenario. A customer was in a pre-migration lab. They were testing, they were doing performance testing of virtual host provisioning, meaning, hey, a new VM spins up, it reaches out to a provisioning server, says, hey, what am I? Who am I? How should I, send me packages, let me build myself. So basically a host provisioning, automated host provisioning mechanism. And the performance in the lab was so bad that they had to halt their migration. They were actually migrating to Amazon, and they wanted to get virtual provisioning up and running, and they had to halt it because they couldn't get past a performance test in their lab. So inside the lab, here's the new VMs that say, hey, I'm a new VM, somebody tell me what I should be loading. This is in what's called their public zone. And in the management zone was an image server. And in between these two zones, one IPS, one firewall, some mock internet, another firewall, another IPS. So they went to great lengths to really create in the lab environment what they were going to have in production, which, by the way, is just the right way to do performance testing when you can. And notice there's little magnifying glasses. Those are there to say, hey, we took a packet capture close to the host in the public zone and another capture at the same time in the host next to the management zone. So we got to see both sender side view and receiver side view. So there's a lot of vendors in that picture. I didn't put vendor names on. Everybody's pointing fingers, as you might expect. And our task was to help the customer figure out why throughput was so low and help identify the vendor that was causing the problem. So we're going to take, there's tooling that I use that's essentially a wrapper around Wireshark. So I use Wireshark basic stuff, filtering, visualization, all the fields, custom views, all that. But then as part of the toolkit I also use some advanced analytics that rely on what Wireshark produces. So I want to just quickly show you some of those analytics ahead of time. So this is a summary of this is one side or the other, or it was merged. I don't remember. It says management, so it's the management side. And half of the delay in this small sample that I looked at was all protocol delay. So it's got something to do with TCP. Right away, we can see that. And then just some raw statistics. We were trying to move 48 meg. There was 117 retrans, 49 out of sequence, 20 triple duplicate ACKs. So just at a very high level, without even looking at decode, there's trouble in River City. We talked a little bit about bytes in flight earlier. We're just going to quickly review what is bytes in flight all about. So it's the amount of stream bytes that are out on the network before the sender receives an ACK for the leftmost edge of the current burst. And the bigger that number is, and it really does reflect, someone had a great question earlier about the congestion window. It really does reflect the congestion window. Even though we can't see the congestion window as a setting anywhere, we can observe the behavior of bytes in flight, and that'll give us a pretty good idea of what the congestion window looks like. And bullet point being added, yes, it usually reflects the congestion window. So this view, again, this is some advanced analytics. It helps me get to root cause quicker. That chart in the top is bytes in flight. And you can see it goes up, it comes down, it goes up and come down. And every time it goes down, it's in slow start. So let's kind of zoom in to some sections. So here's the beginning. We can see there's slow start happening. We can see triple duplicate ACKs. We can see retransmissions. It continues. And then we just get to a point where it's awful. It's just awful. So what we're going to be looking at as we drill down into these captures and out of sequence and just how bad it was, is what was causing slow start to repeatedly get invoked and the retransmissions, and that's where we're headed. So we're going to look at some decodes. We're going to look at the client side and the server side right next to each other, and let's see how that's going to look here in a second. It's going to be a little bit, I tried to make it easy to follow using graphics, but we are going to have to look closely. So we need, our glasses might need glasses as we jump into this. So here's some ACKs from the client. So this was a random sample. There's a lot of traffic. This is a random sample. And these are the ACKs from the client. There's a couple of things about this decode summary that's worth looking at and pointing out. So basically, by the way, we're only going to look at 19 data packets. That's all. Out of all this 48 meg, we're going to look at 19. We're going to look at how they're arriving. But before we start that, just take a look at, first off, why are there so many ACKs? I thought the receiver is supposed to ACK every other packet. And if you think about it, it's because everything is so out of order that I'm just ACKing everything, which is the first indicator that we've got a mess on our hands. The other indicator is the packet size keeps changing between the values of 66, 78, 86, and 94. And think about what we were saying earlier in the TCP options field. As we get more things out of order and we get more blocks out of order, the TCP options field gets bigger, and then it might shrink, and then it gets bigger, and it might shrink. And these packet sizes reflect, even without looking at the details, these packet sizes reflect the SACK field changing. Let's also look at the receive window. Why is that continuing to shrink? Well, earlier I had a question about how many segments is the receiver holding on to in its receive buffer. And you can see the impact of holding on to too many things. You can see we go from 44K at the top of the screen down to 17K. So that just is a reflection that we're kind of filling up our receive buffer here with all of these out of sequence packets. And then last question, why do we see so many duplicate ACKs? Because we've got a big mess on our hands. There's a lot of things out of order. And we're gonna just take a look at a minute of just how bad is. I'm going to hold questions until we get done with this example. So if anybody's been to Disney, Walt Disney World or Disneyland, hopefully you took a ride on Mr. Toad's Wild Ride. If you didn't, it was a lot of fun, a lot of twists and turns, and that's what we're going to see in our little example here. So we've got one slide for every packet. We're going to highlight some areas and watch what happens to the cumulative ACK field and the SACK field as each packet is received. So here's some orientation for you on what we're going to be looking at. So the column that says pub frame, that is the that's where things were received. Did I say that right? Yes, at closest to the receiver. The column next to it is the frame order as seen from the sender. We're going to highlight in red the packet that just arrived. So whatever you see in red is something that just arrived. Whatever's in green previously arrived, bracketed in green. And again, consider that the mission was to help the customer understand how bad is bad, because it was really bad. And we're going to see that in just a second. You have the TCP header in the bottom, and then we have the SACK field for the packet that just was received. Also down there in the bottom. And what we're going to do is step through each packet that's received and pay attention to cumulative ACK and SACK, and really hopefully cement some of the concepts that we were going through earlier. And I think we have about 5 minutes before the hour is up, and this should only take about 3 to 4 minutes. So we're going to have a wild ride. Fasten your seatbelt. Pay attention or focus your attention on cumulative ACK and the SACK values as each packet is received. And my goal of this exercise is to have you double check, is what we're seeing, does it make sense, that the changes in cumulative ACK and SACK based on what's arriving. So at the beginning of this stream, we're expecting, and the receiver is looking for this stream bytes. It's a big long number. I'm just going to say ending in 6095. And here we go. So the very first packet that was received is actually the third packet that was sent. So notice in the cumulative ACK, we're saying, hey, we were looking for 6095. We didn't get that. We got something else. And oh, by the way, this is what we got, left edge, right edge, but it's not the one that we needed. So we're going to immediately ACK back to the sender. The next packet that we received is way far down in the stream. 1, 2, 3, 4, 5, 6. It's like 6 packets ahead. And notice now that the cumulative ACK has not changed, but now we have 2 SACK blocks. We have a SACK block representing this top row in green and another SACK block representing the red row that was just received. So we now have 2 gaps in what's been received that are missing, 2 pretty significant gaps. Here comes the third packet as received by the receiver. And notice that it's the one that we were looking for all along, which was 6095, whoops, sorry, 6095, right up there. So we increment the cumulative ACK, but the SACK field does not change. The SACK field does not change because nothing else has changed in terms of what was received farther down in the stream. So third packet came in, it was actually it's the one we were expecting. And look at where the fourth packet is. The fourth packet is way down yonder, farther in the stream. And notice that the right edge has changed to reflect the fact that the new right edge should be 575, because we've received everything up to 574, and 575 is what's being declared by the receiver. Here comes packet 5. Notice it's adjacent to the first packet that we got. The right edge has changed for that block. And also notice, and this is kind of interesting, notice that the order of the blocks has changed. And I've seen this occasionally. Apparently there's no mechanism, there's no requirement that you must maintain the physical order from one ACK to the next of your SACK blocks. So I'll just flip that back for a second. I'll go back to the last frame. Notice that 991 was at the top on this screen. Oh, did I say that wrong? 679, maybe I got myself confused. Okay, the order, I think I had this confused with a different slide. One of the slides it does change. I think I put that arrow in the wrong spot. Next packet comes in. Notice that it fills in a missing bit of stream bytes between 2 blocks. So now that 2706 has arrived, we now can go back down to just 1 SACK block. And now our cumulative ACK is 887. And if we look up here, we now have everything up through 886 and we're ready for 887. So everything is much tidier now. We're down to 1 SACK block. But look at where packet 7 landed. Man, way down the stream. Packet 8, I'm going to go through these kind of quickly. Notice we're now up to 3 SACK blocks. Here's packet 9, still at 3 SACK blocks. Packet 10, still at 3 SACK blocks. Packets 12 and 13 were actually right next to each other, so they were nice and clean. I put them on one slide. In this case, as the red frame was received, we've now gone from 3 SACK blocks down to 2 SACK blocks. Here's packet 15, filling in a gap, and now we have 1 SACK block. This one's kind of interesting because we're now working our way up the sequence stream, and the left edge was updated to reflect that packet 16 has been received. There's packet 17, 18, and you can guess here comes packet 19.
Hey, John, just a heads up, it's time for the Q&A.
Q&A. So I'm almost done here. So this is probably the worst nightmare of out of sequence that I've ever seen. It's a huge mess having to do with buffering somewhere, either in a firewall or an IPS. We finally convinced the IPS vendor that it was their issue. They didn't want to accept that until they saw this illustration of just how bad is. Then they finally said, okay, we're going to look at our code, and they found, you know, lots of coding issues. And IPSs have to hold on to packets in order to do signature matching, and the way they let the packets out was really non-optimal, creating huge performance issues. So let's see. We said here, do we have a couple questions?
Sorry, yes. Hans
Okay.
is asking, what's this App Doctor app? Where can we download or buy it if needed?
Hi, Hans. Thank you for your question. It's a Riverbed product called Transaction Analyzer, and you can either email me or look at riverbed.com. I show it because it's part of my toolkit when I'm troubleshooting. It helps save me a lot of time. I use it. It complements Wireshark immensely. But I do use both tools, and so riverbed.com, you can read more about it or email me either way. Next question.
Tika is asking, what will happen if there are more than 4 SACKs?
Well, unfortunately, it's the end of the universe as we know it. It's a complete implosion. No, I'm just kidding. So what happens is I think it's going to depend on the stack for the receiver. I'd really have to take a look at the RFC to find out, do we have to maintain what we've already reported, or could I let something that I previously reported, could I let it fall out of the 4 possible SACK blocks in favor of something new that I just received? So one thing's for sure, it won't hold more than 4. So either I'm not going to report what I just received, or I'm going to have to sacrifice something that I previously reported. And I think that the RFC would be the guiding, you know, there'll be something in the RFC about that. IPS is not stateful like a firewall. Well, it's not stateful like from the standpoint of a connection. Like firewalls, I think of them as being stateful for the life of the connection. IPSs, I believe, I'm not an IPS expert, you know, they're trying to do signature matching, and if a particular pattern they're looking for is split across multiple packets, they're going to have to hold on to enough of those packets to match a signature before they let them out on the external interface. And I think it's going to depend on how the IPS is configured, because if you think about it, some customers would say, I don't want my IPS to let loose something like the first 2 packets of something that are potentially malicious, even though I might not know it until packet 3. And I'm kind of using those packet numbers arbitrarily. So I think it's always going to depend, but I think of IPSs as being stateful from a signature standpoint, but not from a connection. the life of a connection standpoint. Email address is jpittle@riverbed.com. Also john.pittle@riverbed.com. So in this case, the constant input buffering of these incomplete SACK blocks can lead to packet loss if we run out of buffer. Have you seen a SACK issue so bad? Input discard. Well, so that's a great question. We looked at 19 ACKs and we saw that during this crazy period for those 19 ACKs, we got all the way down to 17K of receive buffer. If that had continued and we got down to smaller than a segment size, then the sender would have had to stop sending. And here's where you kind of get into a deadlock situation. If the sender stops sending and I can't retransmit something that's missing, then what? Then I'm not sure exactly what, I've never seen that, but I can envision where that could potentially happen. Okay, have you seen similar multi-SACK behavior in wireless networks? Yeah, absolutely. There's a lot of packet loss in wireless networks just as a matter of course, just because it's a very contentious medium. So yes, I have seen that, but let me back up a second, because I didn't answer that the right way. I apologize. So there's a lot of packet loss inherent in wireless, but those retransmissions are being handled by the wireless components of that infrastructure. So they'll do an 802.11 retransmit. There's no concept of SACK in wireless. And if the retransmits, you know, I've just recently spent some time doing some wireless troubleshooting. It was very eye-opening. I didn't see a lot, what I saw a lot of was packet loss and very, very high latency. And some of that high latency was due to not being able to transmit over the air because the airwave was busy. A lot of noise, a lot of signal loss. So I saw more retransmissions, not so much out of sequence packets in that case. Okay, so let's see. ACE got renamed to Transaction Analyzer. That is correct. The name is not changing, but there's an updated version due out at some point soon. It might have come out already in, updates, a few new features. So that's on its way, yep. And then just to be clear, what we were looking at the 19 packets you've just shown, you put the TPs in order, ignoring the order the frames were received, correct? Is this if we want to see something like this? You know, I put that together kind of like a kaleidoscope effect. I wanted to be able to show the customer packets are not just a little out of order, they're a lot out of order. I mean, jumping 5 packets ahead, coming back 3 packets behind, jumping back again, it was just a mess. And when I was looking at the decodes, it's like, I have to draw a picture of this. And then I was kind of struggling with how do I draw a picture of this? Because when you just look at the numbers, the sequence numbers, and you look at the left edge and the right edge, it's not, at least for my brain, it doesn't quite cement just how crazy the out of sequence was until I was able to get to that animation. And I've used that animation in training, you know, I used it for the customer. I've used it in training exercises. It took a long time to to put it together and validate it, but it's been worth it. So there's not any other way that I know of to really visualize that. So that's why I say focus on in-flight bytes, because if in-flight bytes stays high, then there's no impact to the out of sequence packets, no meaningful impact. But if you see you dropping down to slow start, coming back up again, dropping back down to slow start over and over again, then yeah, it's impacting performance and we need to understand it. And chances are it's not just a simple little load balancing issue, whether it's packet load balancing or session load balancing, you know, it's something bigger than that. And in this case, it was an IPS. let's see. So for the packets in the SACK blocks, even though the packets have been acknowledged, they aren't handed over to the app until the missing packets. That is correct because TCP guarantees the application. I will only deliver to you stream bytes that are in order. It's a guarantee. So the TCP stack has to buffer everything it receives until it's got everything in order, and then it can hand it off to the app layer. And you know, things like the push bit and urgent bit might influence when that happens once it's all in order, but until it's in order, the push flag means nothing. I mean, that's my opinion. Somebody might disagree with me, but I can't imagine how, even if there's a push flag of something that's out of order, you can't give it up to the app because it's not in order. Not with TCP. With UDP, you could, you know, UDP doesn't care. TCP would care. Okay, when do congestion algorithms kick in? Whenever there's retransmission is the answer to that. And seems SACK was designed to solve problems like this. Yes, so how bad would this have been without SACK? Well, you know, that's a good question too. I kind of think that, let's say SACK was not enabled, there'd just be retransmissions all over the place, just like there is now, because there's so many triple duplicate ACKs, it's generating retransmissions, which is closing the congestion window. The thing about not having SACK is you would not know what was received. So the nice thing about having, so your question, how bad would it have been without SACK? I would say then you have no real opportunity of knowing what was received. At least you wouldn't, there'd be no way for the sender to know because the receiver would not report it. And then you'd have to hand jam everything, kind of like I did with that Excel, with that view that I created. Feature request for Wireshark, maybe it could draw the same picture of a TCP stream. You know, I think that could be very interesting too, but what I've noticed, and it might take some work, in-flight bytes changes behavior for retransmissions. And when I say changes behavior, what I mean is it's not exactly like I thought it might even increment because I have put more bytes on the network, but it's retransmitted bytes. So maybe in-flight bytes is not meant to include retransmitted bytes, but yeah, and I did not look at the TCP stream. So that might be actually very interesting to see if it's really moving around, you know, going up, coming down, going up, coming down. That could be very interesting too. Would an IO graph showing SACK count over time be a good way to look at times when? Yeah, absolutely, because you would, the only thing about that, and what you'd have to do is probably do max. What is the max value in any 1 second interval? Because let's say there were 10 SACKs in a 1 second interval, your choices are minimum, average, maximum. And there might even be a count. If there's a count, and that might be what load means. If there's a count field, then just knowing that how many packets had SACK without necessarily knowing how many blocks per packet, that could also be interesting. And using the colorization, I think could be very useful as well. And I'm noticing, okay, we've got like 3 minutes.
Yeah, we have 2 minutes.
2 minutes, okay. So to see the delay that's introduced when SACK is in play, with setting a time reference in the first packet where SACK started and then looking at a time when the missing packets show up. Well, I think what you would do is actually put the, set the reference time in the first packet, how do I say this? The segment that was sent that was not received. Because if you think back to that crazy picture where we're bouncing all over the place, we were actually like 6 or 7 packets ahead of where we should have been, you know, showing up at the receiver. So I think you would, and you kind of have to do this multiple times to get a perspective. But if the first segment that was retransmitted, you'd have to go back to where it was originally sent and set the time reference there. But it's a really good question and a good strategy. I think you have to kind of play with it a little bit. So I can't believe we're done already. I could go on. I've got about 10 more slides, but we're not going to use them.
You can continue on Discord if you want in the Zoom 1 discussion channel.
Well, I appreciate that option, but I'm like ready to have dinner. Sorry.
Right. Fair enough.
But this is going to be posted, right? The deck will be posted. I know the video will be posted. Will the deck be posted also, Angelo?
Yep. As soon as you send it over, yeah. Yep,
I'll send that over. So thank you everybody for attending this session. I don't know how many people we had. What was our count? This might be the biggest audience for this session. Was there like 5,000 people?
There were about 70, I think, 75.
Oh, that's exciting. Thank you everybody for attending. It really means a lot to me that you're interested in this topic. It's helpful to understand these concepts. And I wish you all the best in your troubleshooting. And jpittle@riverbed.com. Feel free to email me if you like. And see you at the next SharkFest, or hopefully. And next session, I've got one tomorrow night on an overview of WAN optimization. So thank you. Bye.